Okay, let's have a look at how to do this buffer calculation. First thing we could do is reminding ourselves of the equation we need to use to work out the hydrogen ion concentration. I'll write that at the top now. Now this buffer solution is made by getting some sodium hydroxide and adding it to propanoic acid. So let's write the chemical equation for that, and that will help us work out the number of moles. So I think the first step should be to work out the number of moles of sodium hydroxide and the number of moles of propanoic acid. And let's write that underneath the formulae in the chemical equation. Now obviously there's an excess of propanoic acid, there has to be. Because remember, a buffer solution, an acidic buffer should I say, is a weak acid plus its conjugate base meaning the salt of the acid. And by that I mean this stuff here. So let's work out the number of moles that we've got left when the reaction's happened. Okay, so once the reaction's happened, we've got these numbers of moles. Now think about the equation at the top. We need the concentration of propanoic acid and we need the concentration of propanoate ions. So therefore the numbers of moles that we need is this one here and this one here. So the equation H plus equals Ka multiplied by the concentration of propanoic acid divided by the concentration of propanoate ions. Now, we could divide by the volume in dm cubed. We've got 35 centimetres cubed there, so 35 divided by 1,000. However, we don't need to bother because that would cancel out. So therefore, we can put everything into this equation. Now, if I put that all in my calculator, I get 2.67 times 10 to the minus 5. So 2.67 times 10 to the minus 5 moles per dm cubed. Now remember, I'm going to leave the full precision value in my calculator and I'm not going to round till the end. So if I take log to the base 10 of that and then I change the sign, I get a pH of 4.57. And that is the pH in my buffer solution. Now, if we have a check back, does that seem reasonable for an acidic buffer? Well, it does, because it's a weak acid plus a conjugate base, the conjugate base being a salt of that acid. Okay, the last and final question. So a small amount of hydrochloric acid is added to the buffer solution. Explain why the pH of the buffer solution stays almost constant. Now, almost constant is absolutely key. When I do a question like this, I like to write the equation. So CH3 CH2, COOH, and that gives us CH3, CH2, COO minus plus H plus. Now, if we add a small amount of hydrochloric acid, what's going to happen is the position of equilibrium is going to go in this direction. And the reason for that is we've got a large reservoir of the propanoate ion, this stuff, and also of propanoic acid. So let's have a think what the marking points are going to be. So you could say this equilibrium shifts to the left to remove the added hydrogen ions, and therefore you can say that the hydrogen ion concentration remains approximately constant or almost constant, referring back to this key term here in the question. So let's put pen to paper and let's answer that. So the first marking point, equilibrium shifts to the left to remove the added hydrogen ions, and therefore the concentration of hydrogen ions remains almost constant, and that's key there. Right, hope that's helped.